Hello everyone, my name is Okan Seker from University of Lübeck, and today I will talk about our joint work with Tim Gellerson and Thomas Eisenberg, differential power analysis of picnic signature scheme. It's a well-known fact that embedded devices that run a cryptographic algorithm are vulnerable to physical attacks. So let's assume that we have an adversary Eve, so she will be our adversary in this presentation. She can use such information such as power, timing, or she can just use an active attack and implement a fault injection. In a very basic scenario, she can just reveal the secret key using a differential power analysis. However, these results are known since the emergence of the seminal work by Kochor et al. In 1998. The main reason that we would like to revisit these attacks is the ongoing NIST post-quantum project. As you know, the competition is in the third round and there is a fourth round on the horizon. So here we can see a summary of the finalists and alternate candidates. So this research is motivated by the fact that the such-channel resistance of cryptographic schemes is becoming more and more relevant as they are deployed in real-world conditions, and it is one of the most important evaluation criteria of the NIST PQC standardization process. In this work, we focus on PICNIC, which is an alternate candidate in the NIST PQC project. So let us briefly recap the current state of the art. PICNIC is a Fiat-Shamir type signature derived from the MPC-Indeed zero-knowledge proof. It has a couple of nice features. For example, its security doesn't rely on any number theoretic assumptions. Essentially, the only assumption that we need are the security of block cipher and the hash function that is modeled as a random oracle. So it also supports various parameters and different signing methods. So in this work, we are not focusing on other variants, but there exist different PICNIC signatures that provide trade-off between size and speed. So we focus actually on the foundation of PICNIC in this presentation, the zero-knowledge for Boolean secrets, ZK-Boo, and its optimized version ZK-Boo++, and more explicitly speaking, MPC-Indeed paradigm. So we study the applicability of such-channel attacks protocols relying on the MPC-Indeed paradigm and described these attacks in details. So we have shown two practical attacks to recover this secret key and the multiparty computation of LowMC algorithm. The first attack exploits the secret sharing process, and the second attack uses the multiparty computation of the SBox layer. Moreover, we give a description of the practical setup with physical embedded implementation on the Freedom board with Cortex M4, and implement the PICNIC signature scheme using the official repo. So we choose the electromagnetic emission of the device as our side-channel source. And finally, we give a novel algebraic key recovery part to reconstruct the key. So what we are going to show in this presentation is first of all, we take a look at our motivation and give the basis of LowMC, which is the key component of PICNIC, and ZK-Boo, which again provides the zero-knowledge proof of PICNIC signatures, and we take a look how the attacks actually working against ZK-Boo. So then we continue with the attack descriptions, and this is followed by the description of practical setup and experimental results. And finally, we give the algebraic key recovery, and then we conclude our presentation. So let's start with the symmetric key primitive of PICNIC signature, which is LowMC block cipher. So when we go into details of the block cipher, we see a very simple structure. Here we can see the picture taken from the LowMC documentation. It has four main layers basically, which is the key addition, constant addition, linear, and the SBox layer. It is a very low end depth, so the SBox only 3 by 3, and it's a very low end depth, and which makes it suitable for the multiparty computation. SBox layer is only the nonlinear layer. Therefore, during MPC computations, only in this area where we need the communication between the players. So the values corresponding to this layer are opened during the verification phase, which we will actually describe more detail in the following slides. And we will use this fact in our attacks. So, but there is one caveat here. As you can see, there is only 30-bit goes into the SBox layer, which causes us some problems. However, at the end of the presentation, we will describe how to overcome this issue with the attacks on the deeper rounds. So let's see how the MPC in the head actually working. So as we said, this is the zero knowledge proof part of the picnic signature scheme. So the idea is simple. We have a public function phi and a secret value x, and which produce again a public value y. And the idea is to split this computation into 3 branches. As you can see, we have 2 main functions here. We have the share and reconstruct. And the third component is the circuit computations, which are XOR or AND operations. The share functions, as the name suggests, gets a secret value and produce a sharing of x, and the reconstruction is just to sum the output values and to produce output y. The first thing, of course, is the multiparty computation should be correct. And the main idea of the MPC in the head is revealing 2 branches. 2 branches will not reveal any information about the x. And therefore, this can be used as a zero knowledge proof. And as I described, we can just reveal the computations, reveal just 2 branches of our circuit decomposition, and prove the knowledge of the x value. So, and the values derived while generating the signature, as we are going to describe in the next slide. So, in picnic case, this phi function is selected as LowMC, which inputs the same plain text and the same secret key for each repetition. So now let us combine what we have seen and describe the basis of picnic. So in this figure, we can see an overview of the signature scheme. So the highlighted area with the green area shows us our target, the multiparty MPC, multiparty LowMC calculations. So in this area, as you can see, the multiple repetitions of MPC-LowMC is implemented. So explicitly speaking, there exist 219 repetitions. And for each repetition, a challenge is derived. Here you can see the values from E1 to A1. So that means for each iteration, we are opening a subset of the branches as we just described in the previous slides. So the challenge points us which values are going to open. However, each repetition uses the same plaintext and the same secret key. So the rest of the scheme corresponds to the commitments, hashing, etc. And since we would like to focus on MPC-LowMC and the challenges, we just choose to focus on this area, as the secret key of the signature scheme is actually used in this area. So now let us go back to Zcabu again. As we left, the last time we left, we opened 2 branches, right? So as the protocol itself. So you see how Eve can actually see the open values as free probes. Clearly, she can read the revealed values due to the protocol itself. And using this information, she can just probe a variable in the unopened branch, and this will leak information. So, and using this idea, we will describe our attacks. So let us focus on the first attack. So this attack uses the calculations of the secret sharing process or the share function, as we just see. So the implementation of this operation is done randomly sampling the key shares of first 2 players. Using these values, the key share of the third player is calculated as in this equation. So critical thing is, during the challenge and opening phase of the picnic scheme, the key shares of these 2 of the 3 players are revealed and become the part of the signature, which we described as free probes in the previous slides. So in the following example, let's focus on a single challenge, let's say C0, which reveals the key shares of the first and second player. In this case, the key shares of unopened player key 2 is a product of 2 chained XOR. The first XOR is with the secret key S, and the first key share key 0, which is then stored in register R. So the second XOR is the value in the register with the second key share key 1. So the resulting value corresponds to the final key share key 2. So therefore, we can transfer a key guess on secret key S on a key guess on key 2, which is supposed to be secret. The second attack is on the SVAX layer, on the SVAX calculation. So why we choose this layer? Because, as we talked before, the only nonlinear layer of LowMC is the of LowMC. So this layer is only the lonely only lonely layer of LowMC, and therefore there should be a communication between players. We denote the MPC-LowMC with the players of this operation by capital P0, P1, and P2, and their states as small p0, p1, and p2. You can see that we further denote the theoretical unshared player as capital P and its state as small p. Moreover, the dashed values are not revealed. So therefore, what we need is to just formalize these unopened variables using the opened ones. So again, we focus on a single challenge where the state P0 and P1 are opened. Using this correctness of these equations, we can successfully implement the key guess. So, in summary, what we have shown that we can exploit the MPC net structure of picnic signature scheme by focusing on two different parts of the algorithm. So clearly, these explanations are theoretical, and sometimes it's hard to digest in 10 minutes. So we need a saver, which is the practical setup. So in the next, we focus on not only our theoretical setup, but with a practical setup and give the experimental results. So first, we would like to introduce our practical setup. So in this picture, you can see an overview of our setup. Our capturing device, we have used a Tektronix MSO6 with 320.5 sampling rates. As our target device, we have used the Freedom board with Cortex M4 clocked at 120 MHz. So, as our side channel source, we have chosen a blocking capacitor as seen in the picture and placed the electromagnetic probe close to this point. So, why we have chosen this? Because this capacitor represents the power consumption best. Let's first take a quick look at the sample trace. Here you can see a single round of MPC-LowMC structure. It starts with the secret sharing, which will be our first target in the following slides, and the algorithm continues with the key whitening and other linear layers of LowMC, as we described in the previous slides. So the second interesting area is actually at the end of the trace, where we can see 10 S-box calculation individually. So you can see the labels, and this area where we will focus for our second attack. Okay, as our first step, we would like to verify this leakage first of all, and this can be done by a simple leakage analysis test. So as our test tool, we have used TVLA, which is Test Vector Leakage Assessment. So this is a simple statistical tool that is used in the literature for leakage analysis. It's a pass-fail test to determine if an implementation has a leakage or not. So what we call in this case as a leakage is the data-dependent behavior of the device. So there are two different versions of test. Although we are not using the first one in our analysis, I would like to describe it in order to capture the essence of leakage analysis. The first one is fixed versus random. This one is to detect all first-order leakages of a device. So the idea is to process either fixed or random data. So as you can see in this example, we can just select a fixed plaintext, and in this case it's all zeros, or choose a random plaintext and compare the sidechain information. Therefore, this give you a data dependency through the implementation by comparing the traces belonging to a fixed data with the traces belonging to a random data. And the second one is random versus random. In this case, we always process the random data. However, the classification depends on a single bit inside the implementation. Therefore, the second method is used to observe specific target in an implementation. And as our leakage verification, we used random versus random test. In this analysis, we use the open values from the 10th S-box, and to the classification using the open values as highlighted in this slide. That is, we compare the traces classified by the value of A0 XOR A1. So remark that this analysis can be done with any of the open values for the same calculation. So the leakage is clear and can be seen in this case, and as the maximum absolute T value exceeds 4.5 even with 6,000 traces. And if we choose a different open values, this peak will be shifted, so that will be only difference. Since we verify that picnic is indeed variable, let's take a look to the key recovery attacks. So here you can see the player results with 20,000 traces. Although this graph we cannot see any difference on a single pick. And also you can see our power model here, and for each candidate we use this formula to calculate the Hamming weight, and which gives us a model for our power consumption of the device. But when we take a look at the maximum correlation with respect to the number of traces, the correct key indeed gives us the highest results. And moreover, the correct key is actually distinguishable with less than 2,000 traces. Remark that every signature we have some repetitions, right? So we have 219 repetitions. And when we select the repetitions that gives us the same challenge, for example, let's choose the same MPC-LowMC repetitions for challenge C0, and this will give us roughly 30 signatures. So when we collect the 30 signatures, we will have 2,000 traces, roughly 2,000 traces that belongs to the same challenge. And therefore, we can use the open values for those traces. When we look at the second attack, we see a similar pattern here. Here we can see 3 bits of the same S-box. Although we can see 2 symmetrical lines here, the highest negative value gives us the correct bit, and this is just because of the position of our electromagnetic probe. So when we take a look to the change of the values with respect to the number of traces, the success of the attack is much clearer. The highest negative values are clearly distinguishable with 2,000 traces, and similarly, as in the previous attack, we can get the correct key. That means using 30 individual signatures. Okay, now what we discussed until here is how to reveal the key related informations. But as I described before, now there's a caveat, right? So we know that due to the LowMC structure, there is only 30 bits goes into the S-box layer, and that leaves us 30 bits of the round key. But this is actually not enough to get the 128-bit key recovery for the secret key. But the good news is we can repeat the attack on the deeper rounds of LowMC. So due to the MPC index structure, the values are open for each round, and the key related values for each round are actually revealed. Here you can see the DPA attack on the second round S-box layer, and clearly the images are similar and what we have shown. So what does this mean? We are actually getting from the attacks on the deeper rounds is actually a system of linear equations as given in the slide. So this is just U times secret key equal to V. So secret key is key S, and it's 128-bit, and U is derived from the LowMC structure, and V is derived from the attacks. And R you can think about as the number of rounds that the adversary is attacking. So every round we are getting 30-bit information. Therefore, for every round, what we are getting is actually 30 rows of U, and that's all we need basically. We need to just fill this system of linear equations and solve it. Of course, we can just solve the equation uniquely. To solve this equation, what we need is 128 independent equations, right? Of course, we can go like 5 rounds and have 150 equations that satisfies this equation, or just attack on the 4 rounds and brute force the last 8 bits, and the solution just can be done by a simple Gaussian elimination. So, in conclusion, what we have shown is the side channel analysis on protocol level is a real threat, and MPC in the head does not necessarily provide security, since the open values give the adversary additional information. What we have shown with these 2 attacks on 2 different stages of picnic signature scheme that leads us to full key recovery. And additionally, what we have shown is a novel algebraic key recovery to combine these attacks. So thank you for your attention. If you have any questions, please feel free to contact us, or if you are more interested, you can get more details in our ePrint. Thank you.